Hi everyone, I hope you're all doing well today. Welcome to my workshop. Today I brought you a really interesting topic. We're going to talk about free heating. Yes, it will be free, but first you have to invest a little. There's a solid physical basis for this. That's what I'm going to tell you about first. In 1821, Seebeck discovered something very interesting. If two different metals are in contact with each other and the two metals are at different temperatures, a voltage is generated between them. A little later, in 1834, Peltier discovered the opposite effect. From this perspective, the opposite effect means that if you apply a voltage to two different metals, as a result, one metal heats up while the other cools down. This is very interesting. So, what I just described means that there is a physical phenomenon that can basically convert a temperature difference into electrical energy. And of course, it also works the other way around. We are able to create a temperature difference from voltage without any moving parts. That's why I bought a Peltier element, and I built the Peltier element into this. The Peltier element basically looks like a sandwich. There's a ceramic layer on top, a ceramic layer on the bottom, and in between there are small units called Peltier elements. If I start cooling the top part, for example, and heating the bottom part, then a voltage is generated between the electrical connections. So I'm not going to use the Peltier effect now, but rather the Seebeck effect. It's just that the module I use to extract the energy is called a Peltier element. But in practice, I'm going to use it as a Seebeck element, which means that if I create a temperature difference, the Seebeck element will generate an electric voltage. Behind me here, you can see a rod that's a whole 6/10 of a meter long. It's insulated. This black part here is the insulation, and inside it, there's what's called a heat pipe. In short, a heat pipe is a copper tube filled with gas. Inside the copper tube, there's low pressure, and it contains a liquid with a very low boiling point. On this side, right here, you can clearly see a heat sink. This heat sink is made of aluminum, and now I'll turn it over slowly. And here, at the other end of the heat pipe, there's a copper block wrapped in insulating material. Here we have an aluminum heat sink, an aluminum cooling block, a Peltier element, a copper block wrapped in insulating material, and here is a very, 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 very long section. The copper pipe is insulated, and here this part is without insulation. This part is exposed to the temperature of the ground, 7, 8, 9 degrees, depending on what the temperature is at 1.6 meters deep. The acetone that is inside here will begin to boil at this particular temperature, and as it does so, it will carry the heat energy upwards to the head unit that you can see right here. This process then heats up the copper block that is located behind the Armorflex insulation here, thereby creating a temperature difference between the two areas. So here it'll be the ambient temperature. If the air temperature outside is 0 degrees, then it'll be 0 degrees here as well. If the ground temperature is roughly, say, 8 degrees, then the temperature of this head unit here will be about 6 or 7 degrees, and between the two, there will be a temperature difference of about 6 degrees. From this 6-degree difference, electrical energy can be generated. So I drilled a 1.5 meter deep hole in the ground in the garden. The first meter was easy because I had a drill bit that was 1 meter long. I extended the remaining half meter using an aluminum rod. So this way I ended up with a 1.5 meter deep hole. As I mentioned, it's a full 1.6 meters, with the last 10 to 15 centimeters sticking out of the ground. I found that the soil temperature was 9 degrees Celsius. The air temperature at the time was around 1 degree Celsius, so the system automatically brought up heat from the ground below, meaning it managed to bring up the 9 degrees needed, though only with some loss along the way. There was about a 2-degree loss, and in this area, the temperature ended up being roughly 7 degrees. This Peltier element that I used consists of about 300 individual units. These 300 individual units are connected in series. With the effect of 6 degrees, I managed to generate a voltage of about 200 millivolts. As you can see, this isn't a particularly high voltage. It was actually just 0.2 volts. This voltage corresponds to a current of about 100 milliamps. If we look at the power, that's only 20 milliwatts. That's really, really little. But I actually have some good news for you. The colder it gets, the more energy it can deliver. The colder the environment is, the more effectively this heat sink cools down, primarily due to the temperature of the surrounding air. The colder the air is and the greater the temperature difference between the copper block and the aluminum heat sink, the more voltage it can generate. So if the temperature difference between the two isn't 6 degrees but 12 degrees, then the previously mentioned 200 millivolts of voltage will immediately become 400 millivolts. The voltage produced by this Peltier element increases roughly linearly with the temperature difference. Obviously, you can't heat a family house with just a single rod like this. You'd need to drive in several thousand rods. Fortunately, it works in such a way that you can add them together, so the voltage generated can be connected in series, and one rod can deliver, say, 200 millivolts or 400 millivolts. It depends on how big the temperature difference is. For example, if someone sticks 1,000 rods into the ground, that already gives you 400 volts. Let's look at the budget for this whole thing. Right now, for me, it's around 4,000 for us. This includes the price of the copper rod, the copper block, the aluminum heat sink, the Peltier element, and even the 900 forint acetone, which you can more or less see on the screen. I brought out a spotlight. Here, you can see that the system is generating 218 millivolts. Here, you can see the temperatures, so the top one shows the air temperature. That's 1 degree, 7.3 degrees at the top in the heat pipe, and 9.2 at the bottom. And here you can see the heat pipe that's been staked into the ground. Here, the air temperature is 1 degree, so what you see here is about 1 degree. This part, this heat sink along with it, this aluminum block here, is roughly 7 degrees, and as a result, about 200 millivolts of voltage was generated. There are currently no moving parts in this whole setup. Specifically, it was successful in that I managed to generate energy without any moving parts at all. As you know, I took advantage of the fact that at a depth of 1.5 meters, the soil temperature is roughly 8 or 9 degrees. And I also made use of the fact that in my experiment, the air temperature was 1 degree Celsius. If it had been minus 5 degrees, that would have been even better. I could have generated even more energy, although the amount of energy produced wasn't particularly high. In any case, I was really curious to see if this was possible. And now I'll tell you, yeah, it's possible. You saw the evidence. You just have to be clever and think things through. So that's what I'll keep doing in the future. So thank you for watching my video. Bye. Hello, hello.